Right, welcome back. I hope you got to know some new friends, new people. Jeff, computer architecture, something I happen to like. Jeff said, let's wait 10, 20 years, and that's part of the solution. And perhaps the talks in this session will give us an idea whether some architectural help from computer engineers might help with some of these problems. Let's start off with our first speaker, Steve Furber from the University of Manchester.
Thank you for that introduction, Andy. This first slide just has a few acknowledgements to the sponsors of the work I want to describe. The construction of the machine was funded entirely by EPSRC, and the machine is now, operation is being funded through the European Research Council and the EU Human Brain Project. Now, the last time I stood up here, a couple of months ago, it was to deliver the British Computer Society Lovelace Lecture, and indeed on that occasion I was introduced by Professor Andy Hopper. So this is becoming a habit, Andy. As part of the Lovelace Lecture, I did a little bit of homework, and Ursula Martin pointed out a very useful quote from Ada Lovelace, and this is the 200th anniversary of her birth. Ada Lovelace, of course, is known as the world's first computer programmer, although there's a little bit of debate around the factuality of that. But in her notes, she wrote this thought that she had her hopes, and very distinct ones too, of one day getting cerebral phenomena such that I can put them into mathematical equations, and so on. A high ambition. Unfortunately, Ada only lived to the tender age of 36. Had she lived a little bit longer and fulfilled this hope, she'd have saved a lot of us a lot of trouble. If we look to a slightly more recent point in time, 60 years ago, the semi-detached house at the top left of this picture, which is about 1.5 miles from where I live to the south of Manchester, near Manchester Airport, there's the blue plaque highlighting the fact that this was the house where Alan Turing spent his last few years while he was up in Manchester, and it notes that he was the founder of computer science and cryptographer. While he was in Manchester, Turing worked on a number of things, but most notably for the purposes of today's discussion, he wrote the seminal paper published in Mind on computing machinery and intelligence, where he starts by saying, I propose to consider the question, can machines think? And then turned this question around into something that was more scientifically specified, which he called the imitation game, but which we all know simply as the Turing test for machine intelligence. Now, in this paper, Turing hypothesized that all that would be required for a machine to display human levels of intelligence was that it should have more memory than the Manchester baby machine, which was the machine that drew him to Manchester in the first place. He predicted that by the end of the last century, machines might perhaps have 1 gigabyte of memory, which was a remarkably accurate prediction when you consider that he made this just a couple of years after the baby machine first started operating, and the baby had about 128 bytes of memory. So extrapolating to 1 gigabyte, and indeed it was around the turn of the century when the computer on your desk would have about 1 gigabyte of main memory. But he thought the Manchester baby was entirely powerful enough to pass his test. All it needed was more memory, and by the turn of the century it had that memory, and it was perhaps 1 million times faster, and yet still no machine has convincingly passed the Turing test today. Alan Turing would be very surprised at that fact. There was some debate as to whether a few months ago a particular program did or didn't come close at a Turing test that was run in this building. But I still feel it's true to say that no machine has convincingly passed the Turing test. And my take on that is that the reason it's been so difficult to endow machines with the kind of intelligence that we see in humans is that we've not really worked out what the foundations of human intelligence are. And so the work I want to talk about is going back to look at the basis of human intelligence, which is the human brain, and see if we can understand more about that. Before I start, just a little bit of historical state. This is why Turing came to Manchester. Freddie Williams and Tom Kilburn, pictured here, had built the first machine that implemented Turing's big idea from the 1930s of the universal computing machine. And that was in 1948. Just 60-odd years later, Manchester has been building computers ever since, and this is the latest one that I'm going to say a little bit more about in a moment. But for the purposes of this point of the talk, you can think of this as just a typical modern, reasonably energy-efficient processor computing system. This one's built into the Spinnaker machine. If we compare those two machines, Baby used about 3.5 kilowatts of power with which it would execute 700 instructions a second, and so it used about 5 joules per instruction. A modern processor, such as the one on Spinnaker, in this case uses 40 milliwatts. It executes some 200 million instructions a second, and the ratio of the energy consumption per instruction of those two machines is this enormous 25 billion number. So the energy efficiency of computers has improved by a factor 25 billion in a little over half a century. One observation here, of course, is that I've used the word instruction twice, and it really hasn't changed much in those 63 years. The Baby machine was a 32-bit binary computer where an instruction would do a 32-bit binary arithmetic operation. The same is true of the ARM processor that we use on Spinnaker. It's a 32-bit machine. The ARM has a rather broader set of instruction options. Baby had 7 instructions. ARMs have hundreds of thousands of instructions, but fundamentally they're doing the same thing. So this is a valid comparison. And it's that enormous increase in energy efficiency that has propelled the ubiquity of computing machines today. Now, with that background, the research I want to describe is motivated by 2 headline questions. Can we use the enormous computing power that's now becoming available to accelerate our understanding of the human brain? The brain remains as one of the great mysteries of science. Okay? We really don't have a satisfactory explanation for how information is processed inside our heads. And that seems to me to be a very big gap in scientific knowledge that we need to fill. And then, as we learn more about how the brain processes information, can we use that to work out how to build better computers? So my research is driven by those 2 headline questions, and because I'm a computer engineer, I build machines. The way I'm addressing these questions is to build a machine to try and answer them. The Spinnaker project has had the objective from the outset of putting 1 million mobile phone processors into a computer, because brain modeling is clearly a massively parallel problem, requires huge amounts of computer power. With 1 million mobile phone processors, we still only get to about 1% of the scale of the human brain. So why stop at 1 million? Well, academic budgets are finite, and 1 million demonstrates the principle of scalability while being just about affordable within a typical academic research budget. And I say 1% of the human brain. Another way of looking at that is 10 whole mouse brains, which sounds rather more encouraging. To build this machine, we have to adopt some principles that tune the machine to the particular problem. One of these principles is that if you look in the brain, you find many different sorts of network topologies. It's not convenient to rewire a machine. We want this machine to be sort of universal when it comes to modeling brains. And so we do the usual computer science thing of virtualizing the topology. So given any network of neurons, you can throw them onto the machine and you can connect them to model the topology you're interested in. The machine is highly parallel, and the thing that kills parallel computation is synchronization. So on Spinnaker, we just don't do it. We run the machine asynchronously, and in every processor, time models itself. And thirdly, and this is more about engineering than the application, I've always believed that energy is a primary resource in computing, and effectively the hardware is free. What costs is the energy to perform the computation. So at the engineering level, the machine is motivated by that view. These things come together, firstly in a piece of silicon. We've designed the machine from the silicon upwards. And there's a microchip here. This is a square centimetre of processed sand. It took about 40 man-years of effort to put the design on this sand, which is reasonably economical by today's industrial standards. One of my claims for doing research in microchips is you get more PhDs to the square millimetre than most other subjects. And indeed, there are I think four or five PhDs somewhere in this picture. And the chip is packaged in a standard, boring black plastic package with an attractive logo. One of the nice features of the name, which is a crude compression of spiking neural network architecture, that's where Spinnaker comes from, is it suggests a very easy to draw logo. And we fold a memory chip using some fairly basic 2.5D integration into the package. So each package has 18 ARM processors and 128 megabytes of DRAM memory, all tuned to this problem. If we look at the chip, then the resources are fairly carefully matched to our understanding of what we're trying to build. I won't go into the details here, but the key innovation in Spinnaker is the red blob in the middle. In Spinnaker, when a neuron spikes, that spike becomes a packet, and that packet is routed through a packet switch network to as many destinations as it's required to go to. And our goal to model biology in real time is to be able to deliver those packets anywhere in the machine in a small fraction of a millisecond. Because the biological equations tend to have millisecond time constants or longer. So this is basically a network routing box, very much simplified and implemented in 4 or 5 square millimeters of silicon at the center of each chip. And that allows us to tile the world with these chips and make systems as large as we want them to be. The goal has been to aim for 1 million processors with which we can model up to 1 billion spiking neurons in biological real time. The scaling is achieved by multiplying numbers together. So as this picture suggests, we have 1,000 neurons per ARM core, 18 cores per chip, 48 chips per board, 24 boards per rack, 5 racks per cabinet, and 10 cabinets. And if you do the arithmetic, that comes out to comfortably over the 1 million cores, which was our target. We haven't built the 1 million core machine. We will be delivering a 500,000 core machine as an online service as part of our contribution to the European Human Brain Project. What we have built so far are small prototype systems, the main board, and we've implemented up to a single 19-inch rack which contains 100,000 processors. That's roughly the scale of a mouse brain. I try and word this carefully, so these machines have scales corresponding to the size of brain of some animal. This is not the same as saying, therefore, we can easily model that animal's brain on this machine, because in most cases, we simply don't know enough about the internal structure of those brains. And of course, we are running rather simplified neural models, which abstracts out quite a lot of the biological detail. So I talk about the brain scale to try and avoid upsetting my neuroscience friends. The kind of things you can do with the machine, we heard earlier about probabilistic representation. This is a program one of my research students wrote, which is solving Sudoku on Spinnaker. It's a stochastic network, so there are spikes which kind of capture the probabilities, and as you see the solution emerging, the correct answers are green, the wrong answers were red, they've all gone now, and as the green gets brighter, the network is expressing higher confidence in that particular digit being the right solution in that square. The model here was developed by Wolfgang Maass and his collaborators, and we did the local re-implementation. So because on Spinnaker, neurons are software and synapses are software, we have very flexible ability to model different sorts of neurons, different sorts of learning rules. The thing that's in the hardware is the way we connect them together. Now, we've got systems out with quite a lot of collaborators, about 40 boards out with different groups around the world. This one is the most remote user of Spinnaker in Auckland, New Zealand. I think that's about diagonally through the center of the planet. And they are using Spinnaker in a large-scale big data analysis setup. They have this NewCube system, and that's for analyzing spectrotemporal data. I don't have full details, but that's one of the systems they've put together, and you can see one of the small Spinnaker boards on the right-hand side. And the kind of thing they're doing with this software is analyzing, for example, data you can get from medical measurements around the skull of brain activity. And these particular pictures are showing the differences in brain activity between healthy subjects, addicts on methadone treatment, and addicts on opiates. And you can kind of see patterns here. And what the spiking network is doing in this system is effectively doing dimensionality reduction, because the source data has very high dimensionality. The networks then learn features of that and reduce the dimensionality to the point where you can then present it in a system suitable for human consumption through a visualizer. In the future, we've got some challenges ahead. One model I'm very interested in is the Spawn model developed by Chris Eliasmith at Waterloo. This is a model, a sophisticated neurocognitive model with about 2.5 million neurons in it. And this particular video is showing Spawn solving a simple intelligence test, predicting the next component in a sequence. One of the interesting features of Spawn is that it's multifunctional. It will display different behaviors in response to different prompts. The video is very suggestive of how this is modeling certain subfunctions of the brain. It is a virtual neurocognitive system which has a virtual eye and a virtual arm, and currently it runs on a large cluster system, and it takes 2 to 3 hours to compute each second of real time. And within a couple of months, we are pretty confident now we'll have this running in real time on Spinnaker. And it'll only use about one card frame of board, so about 20,000 processors in a card frame, about 2% of the full machine. Historically, computational neuroscientists have been constrained by computing resources as to what scale model they can build. This model is constrained that way. Our hope for Spinnaker is that we basically push those constraints a long way out, so that if they want to increase the number of neurons in the memory function in Spawn by a factor of 10, that won't affect the performance of the system in any way. It'll continue to run in real time. Now, neuromorphic technology is recently being attracting attention. So we've developed this system. It's not entirely clear to us what the killer app for this stuff is, but for example, the 2014 MIT Technology Review listed neuromorphic chips as one of their 10 top breakthrough technologies, and they say they could soon make computers far more astute about what's going on around them. In a surprisingly similar conclusion, the recent World Economic Forum listed the top 10 emerging technologies for 2015, and neuromorphic technology is in there as well. So there seem to be a lot of technology forecasters who predict that this kind of stuff will find a lot of application in the near future. I'm hoping somebody in the room can help me understand where this is likely to be. As far as I'm concerned, we're building this machine to try and understand the brain. If we could find some commercial application for it on the side, that would of course be of great interest. But if we look at this list, then neuromorphic technology is in there at number 9, but this clearly has application in at least 3 other headings here. So sense and avoid drones could be made much more energy efficient using neuromorphic control. Emergent artificial intelligence is a clear application area. and next-generation robotics, we think, is probably going to be able to use this sort of technology. Within the Human Brain Project, we're certainly planning to do a lot of work with the roboticists in that project. And finally, we're not the only organization looking at this kind of hardware. We have some impressive company. IBM has been not only working on machine learning at the top end with their Watson system, they've also been developing neuromorphic systems at the bottom end, and their recently announced True North chip is a formidable piece of silicon. They get about 1 million neurons onto a single rather large chip, and they have plans to build cognitive systems based on this technology. The Stanford Neurogrid is another large-scale neuromorphic development, and also within the Human Brain Project, our colleagues at Heidelberg are building a neuromorphic system. These are all neuromorphic systems like Spinnaker, but they all have very different optimizations, very different approaches to building models of biological neural systems. And this all comes together, I think, in the context of the general trend towards computer systems becoming more cognitive. I thought about this when I was asked by Nellie Croes, the outgoing Vice President of the European Commission, to contribute to an e-book that she was sponsoring on digital minds. And I decided to write this article entitled The Dawn of Cognition. And I think the neuromorphic work and the machine learning work that we're hearing about today all feed into this idea that machines are moving away from being static objects in the side of the office that speak when they're spoken to, into interactive systems that can sense the world and can affect the world. They have actuators, they have sensors, they can move around in the world and do things. And of course, this has been happening slowly over time, but I sense at the moment it's accelerating quite quickly. The most visible examples of this are the Google driverless car that we've heard about, and robot vacuum cleaners, which have already been mentioned today in the context of Andy's lab. And my view is that we are still stuck in terms of giving these things their full capabilities because we really don't know how animals do it. And if we could crack that and get a reasonable understanding of how animals analyze, process, and store information, then we could accelerate this trend very significantly. So I'll stop there. Thank you very much.
So if we could have some questions for Steve. Jeff.
The notable thing about Spawn is that it doesn't really learn. You have to program it, and then they can compile that into a spiking neural net. And it's very impressive that you're going to be able to speed that up a lot. But it suggests that the reason there's not lots of applications of Spinnaker yet is because it doesn't have a built-in efficient learning algorithm. It can simulate what the brain does after it's learned, and it's very efficient at that. But a criticism of the Human Brain Project in general from people like Jan Leca is that it's not designed around a learning algorithm, and the big successes of deep learning have come from the fact that we've made a learning algorithm efficient, and you don't have one as far as I can see.
We have lots of learning algorithms on Spinnaker.
But the hardware isn't designed to run them efficiently. Is that right?
The hardware is designed to run them flexibly. So if you look at the scale of neuromorphic systems, Spinnaker is at the more flexible, less efficient end of the scale. So we emphasize flexibility because our view is that we do not yet know what the correct neural algorithm is, and we do not yet know what the correct learning algorithm is. And therefore, we want to keep those flexible. When we know what the right choices are, and there may not just be one choice, there may be many choices for different circumstances, then, of course, you can cast them into more efficient hardware. But we have Spinnaker systems that run spike time-dependent plasticity. We have Spinnaker systems that run the KTH Stockholm, BCPNN, Bayesian learning algorithm. We actually, although the machine's tuned and optimized for spiking neurons, we're actually implementing MLP with error back propagation learning as well on Spinnaker. So So basically, because the functions in the machine are software, we can do anything, slightly sloppy term, within constraints. Okay, so nothing is ruled out. But for example, we've optimized the machine for the simpler end of the neuron model spectrum. So for point neuron models, Leakey integrating fire, Izikevich, exponential, adaptive exponential. If you really want to run Hodgkin-Huxley models on the machine, you can probably do it, but it won't be that efficient. And the same is true to some degree of the learning algorithms. If you want a really sophisticated learning algorithm built into the synapse, then you pay for that in terms of efficiency.
Do you think you can run backpropagation efficiently?
Yes, we can run. I mean, we haven't done learning on deep networks. We have run deep networks, spiking deep networks on Spinnaker. We haven't run learning on deep networks on Spinnaker. We have run simple MLP with error backpropagation.
Very good. Can I ask a question of my own?
If you like.
It's about tools, the middleware, or that sort of stuff. Do you see progress in some common ground, libraries or some of the automatic language translation, that sort of stuff to help try new things on this sort of hardware? Or is it going to be invented from scratch?
Tools are crucial. I mean, the machine is an incredibly flexible piece of bare metal, which is completely unapproachable by any normal neuroscientist. So we have to build layers of software, and we have layers of software now that talk a number of the standard languages used at the higher level. So we have tools which will automatically map a Pine neural network description onto the machine, for instance, PYNN being one of the description languages, and obviously we're getting Nengo on there as well, which is what Spawn is described in. But I think you're asking at a slightly different level of tool from that.
Well, a generic tool that perhaps is an extension of current technologies in computer science that has momentum behind it, rather than something that's a little different to what that mainstream. And maybe there isn't such a thing, I don't know.
I'm not aware of anything that fits your description.
Okay, thank you. Oh, okay, one last question. I think we have time, yeah.
Hi, Steve, Richard Morris. One growing area of research in neuroscience, actually using animals, is the area of decision-making. Been some very exciting work done with non-human primates by Mike Shadlin at Columbia, and some of this is now being translated into work with rats and mice. What's interesting about it is that it makes a potential point of contact between what you're trying to develop and some of what Zubin was talking about earlier, in that the kind of tasks are being looked at are situations which involve a lot of uncertainty. Things like delay discounting or how one estimates reward when one is in a position of uncertainty. And people are trying to get a handle on the individual neural mechanisms that might be involved in that. So I don't really have a particular question except to sort of point out that there's a growing point of contact there that's coming from exciting new neuroscience research and the potential that you have with Spinnaker.
Yes, I mean, once that kind of model has been developed into something which we can express in terms of networks of neurons and so on, then that's obviously something that we'd be interested in modeling.
Okay, thank you very much, Steve. So our next speaker is Simon Knowles, who is from the industrial side of things, but I must say he's been behind a number of the UK's most high-tech companies in this sort of computer architecture area. Simon.
Thank you, Andy. I think Simon's going to talk a little bit in a later talk about some future technologies, but today we have just one technology that allows us to do computing at any sort of scale or complexity, and that is silicon. So I'm just going to sort of quickly look at the silicon platforms that we use today to try and implement machine learning. and ask the question, or at least pose the question, without fully answering it, could we build better platforms today out of existing and predictable near-term future silicon technology? You can guess that I think the answer is yes, of course. That, by the way, is the internet. That's not a brain. So I'm sure every speaker today will give you a slightly different take on what it means to be intelligent. And I expect most of you know that even psychologists can't agree on a definition of intelligence. So as a silicon engineer, here's my pragmatic definition from a computing point of view. I think we could judge a machine to be intelligent if it helped us to solve problems which were intractable to algorithm, i.e. problems that necessarily require us to approximate a computing task. And there are possibly more than 3 situations in which that might arise, but I'll suggest these 3. So we know a lot of interesting things, a lot of optimization problems are formally NP-hard, which means there is no algorithm, or at least no algorithm better than exhaustive search, which is usually too expensive, so we'd like to use heuristics and approximations. And we'd like the best answer available in a certain number of seconds or a certain number of joules, probably. The second category is the famous write an algorithm to recognize your mother or your grandmother. An algorithm may exist, it's just that we can't conceive it, or perhaps we have ideas as to how we might write it, but they would take too long. So we need an approximation, or we need to build a machine that learns to do that for us. And then the final one, which to me is the easiest one to understand, is the simple fact that in many problems we don't have enough input data to be certain. And vision is the canonical example of this. Vision is the interpolation of a 3D world from 2D views. There's clearly less information in 2D views than there is in the 3D world, so clearly it's not possible to do that exactly. Now, if a machine could do those things, I would regard it as intelligent. That's my pragmatic definition. All the results that those machines are going to deliver will be approximate, of course. So something will have to decide what to do with the approximate result in order to take an action, whether you regard that as part of intelligence, I leave open. And of course, machines, intelligent machines, like intelligent people, may correctly be wrong, or at least the best guess may be wrong. And we will have to get used to that idea. So we had a question earlier about how exact Jeff's stuff was or could be. I think that's kind of orthogonal. I think intelligence only exists in the presence of uncertainty. And from a computer science point of view, I think this represents the most significant transition in computer science since computers were invented. So up until now, humans have solved problems. They have codified the method of solution of the problem as a program, and they've asked the computer to repeat the process, i.e. run the program. I think what we have now is what I generally refer to as the end of the primacy of the program or the primacy of the algorithm. We'll still have programs. Those programs will specify learning algorithms and inference algorithms. However, what's changed is that there is now a dominant role for a data model. It's a probabilistic data model, and it represents a summary of what the machine has experienced before. If you like, we're endowing machines with the capacity for judgment based on experience. And those two things are elemental to intelligence. Now, these models are going to become the most significant thing in future computers. I think they're going to be bigger in terms of demanding memory and compute performance than the algorithms that run on them. So they will dominate how computers evolve in the Silicon Age and beyond the Silicon Age. So we need to look at the characteristics of those models, and I've written some down here. They're large, generally. We know, and Jeff has reminded us, that billions of parameters may be useful. Even for fairly simple tasks, billions of parameters may be useful. We know in our head we have an awful lot of complexity in our data model. The structures of the models are quite complex. We know hierarchy is useful, we know depth is useful, we know recurrence is useful. We're only just beginning to explore it, we know it's useful. We know that locality is useful in convolutional nets, for example. Now, because they're so large and so complex in structure, they must be sparse. If they were not sparse, then there would simply be too much information for utility. And because they are high-dimensional and sparse, well, sparsity is almost a result of high dimensionality, because they're high-dimensional, if we embed them in a low-dimensional substrate, in particular an addressable one-dimensional memory that we've made out of silicon or magnetic bits on a tape or whatever, then there won't be any locality of access to things that were local to each other in high dimension. And this is a very fundamental property that will change the way that we build machines. Right, final points on the nature of intelligent computing before we get onto the chips. The field is, I don't know, arguably 50 years old, but it's still very young. We're moving extremely quickly. There are lots of things that we know are very poorly understood which we expect to be valuable, like recurrence, for example. And already the canon of algorithms and the canon of structures of models is extremely broad. So probably we don't want to bet on what we're doing today. Probably we want to bet on fundamental characteristics of what we're doing today rather than specific structures or specific algorithms. We know that there is a massive amount of computational work involved in a lot of intelligence tasks. We often read research papers where people have trained their neural network for several months on a vast array of computing equipment. So we know that's a problem. Fortunately, we also know that there's enormous available parallelism in these problems. So we can build, for the first time, enormously parallel computers and expect them to be useful. This is the problem that Mr. Amdahl was looking for. To me, the age of intelligent computing is the age of parallel computing. It's here at last. And the natural representation for these models, because they're sparse and complex, is probably graphs. And in fact, I will refer in later foils to graph machines as the kind of machines we need to process these, whether they're factor graphs a la Chris, or neural networks a la Jeff, or something else. And finally, they are holding essentially large factorized probability distributions. That's their purpose. And probabilities probably require fairly wide dynamic range, but fairly low precision. So floating point at low precision is natural. Now there's a problem with sparsity, or non-locality of access, which is elegantly illustrated by this. This is from Lincoln Labs Journal a couple of years ago. It explores the effect on a conventional silicon server class processor, in fact two different ones, of introducing sparsity into a simple matrix vector problem. You see that there is 1,000x difference in performance between how that machine operates. And the performance here is arithmetic operations per second, say. 1,000x difference caused by going away from something where there was a lot of access locality in memory to a situation where there wasn't. And it's caused by the fact that almost every fiber in the body of today's CPUs and GPUs, computers in general, assumes that there is locality of access, spatial and temporal locality, because that's characterized workloads we've had up until now. It doesn't characterize the future. All silicon processors today are limited by two things. They're not limited by how many transistors we can cram in per square millimeter. I can tell you we can cram more in than we can use. They're not limited by how fast they can go. We can build far faster logic gates than we actually use. What we're limited by are two things. One is how much data can we get near to the logic that processes it. And the second is power. We hit a power limit, a power density limit 10 years ago at 90 nanometers. We're now at 16 nanometers. I'll show you some of the impacts of that. But these are the two problems that we need to tackle in order to produce more efficient machines for any computing workload, but this is the particularly interesting one. So we can build faster logic and build more logic if we work out how to solve those problems. Here are today's, or a couple of today's, big iron machines, you might say. These are probably the two most impressive computing platforms available today. The one on the left is a multi-CPU, the one on the right is a GPU, a graphics processor. Actually, increasingly, there's very little difference between them. They both integrate a number of processors, independent processors, usually a few tens, and each of those processors operates on very wide vectors, 512 bits wide on the left and 1,000 bits wide on the right. They both cram in as many floating point units as they possibly can. That's their mission in life. Fill the silicon die with floating point units. And these die are the biggest die that we can economically make, a bit over a square inch. They also operate at a power level which is the most that we know how to extract from silicon by forced air cooling, about 250 watts of that order. And those numbers have been flat for a long time. Clock rate's been flat, power's been flat, size of chip has been flat. So we've not made any advances on those vectors for at least a decade. Now the interesting thing to me is the ratio between the amount of performance that ends up on the chip and the amount of data we can fetch from off the chip. And because we've filled our chips with floating point units, there's basically no data storage on the chip. So all the data has to come from off the chip. The one on the right is the most interesting, the graphics machine. Graphics is a very, very peculiar workload. And you can see that from that ratio of floating point operations per second to words fetched. So for every piece of data you fetch from the main memory of this system, you have to be able to do 73 floating point operations on it to keep the machine busy. There are very, very few. In fact, I think there's one workload with that characteristic, and that's graphics. The one on the left was built really for high-performance computing, and it has a slightly lower ratio, but still a staggering one. Supercomputers in the 1970s were built on the assumption that you needed a 1-to-1 ratio. Look how far from that we've gone. So how do they perform? Well, here's some examples. This is from University of Florida and Microsoft last year. You can see, I guess you can see the shades there. Ignore the the darkest brown one, but the interesting thing is the mid-brown one is the graphics processors, which we all use to try and accelerate our machine learning workloads. And on sparse, this is sparse matrix vector multiply again, the simplest sparse algorithm you can think of. They are indeed getting about 10 times the performance of conventional server-type CPUs. So it's a good result, and that's why we use them. But a more interesting question is, are they actually being used efficiently? So they do get a 10x speed up, and in some cases I've certainly had people tell me that they're getting a 30x speed up on some of their machine learning workloads. But the interesting question is, okay, so what fraction of the chip's resources are actually being used? And in this case, you can see we are hitting perhaps a couple of tens of gigaflops, and these are 4 to 5 teraflop machines. So they are at best 1 or 2% efficient. That's our opportunity. There are 2 orders of magnitude to be got back here. And the reason why they only hit this level of performance is because you've basically filled the silicon die with arithmetic units with complete disregard to communication. Because the graphics application didn't require it. Machine learning surely requires it. Now, most communication occurs through memory. In fact, almost all memory in a program is used for communication. Very little memory is actually used for the sort of persistent storage of data values. Most of it's used to hold a data value temporarily for another part of the program to pick it up later. In other words, it's communicating in time. So I refer to communication, sometimes I refer to memory sometimes. They are the same thing. And these vector machines, these big compute machines we build today, push very much to the left-hand side of this diagram. They assume that every time I fetch something from a memory structure, I can fetch 1,000 bits of stuff next to it because I'm going to find that useful. Now, if you've taken a high-dimensional structure and embedded it in your 1D memory, then you can bet your bottom dollar that the stuff that's useful isn't next door to the piece that you're about to fetch. And access patterns become very much more complicated. A highly parallel, sparse machine, a machine designed to operate efficiently on graphs, is going to want to do memory accesses that are more like the one on the right, where you do want to fetch lots of components to feed your parallel machine, but they'll be scattered all over the memory. And one thing we often forget when we talk about single instruction, multiple data machines, which is what these vector machines are, is that single instruction also means single memory address, which means that you have to not only have a whole load of data that requires you to do exactly the same instruction on that cycle, but also all the data has to have come from exactly the same place on that cycle. And that's a massive limitation. So we are building machines today which do not suit the memory access motifs that are necessary for arbitrary graphs. I mentioned power, and I've tried to show on this foil the approach to that power ceiling taken by today's chips. So the high peak in the middle is where today's GPUs and multi-CPUs are designed. And the orange bar is the amount of power they devote to their floating point operators, to their arithmetic. And the blue bar is the amount of power they devote to getting data to feed those from off the chip. And they're designed to be able to support maximum throughput of both of those at the same time when burning the maximum amount of power that the chip can dissipate. Now that occurs, or that is designed, around about the 64 floating point operations per word fetched point. And if we move to a more realistic memory access motif for graph-based computing, i.e. closer to 1 word fetched, or 1 floating point operation per word fetched, you can see that the amount of floating point capability we can use falls dramatically. The reason it falls is because we can't fetch data fast enough from memory to allow any more floating point to occur. So that's simply a reciprocal fall-off. So you end up with 1/64th of your floating point resources being used. The same thing occurs on the other side with memory access when you're bound by compute, but there are almost no applications in that space. So it's a very simple story. So what we've done is we've built a machine with all this capability. We've maximized what we can do in a power envelope. And then we are, in this machine learning application, massively underusing the power that we could have used, and we're massively underusing the resources that we've built. You could have used all that spare power there, at least to do something else, like put some of the memory on the chip, and then you wouldn't have to spend so much power going off chip to fetch it. The final thread of the same sort of theme is this. Between about 1990 and mid-2000s, i.e. 15 years, the speed of microprocessors that you found in the computers that you bought, your laptops, your desktops, went up from about 10 megahertz to about 4 gigahertz. So a massive increase driven by Moore's law scaling and Dennard scaling of power. And then in 2005 it stopped at the 90 nanometer generation. And those of you who buy computers may have noticed that they're no faster than they were 10 years ago. And the reason for that is because of this power limit. Now the bad news is it's going to get worse. Moore's law continues, we can cram more and more transistors in, but we cannot bring the voltage down fast enough to keep the power flat. So what we have to do is we have to bring the speed down. And the clock speed of these processors is going to slow down unless we do something about this. In other words, by cramming more and more floating point units into a silicon design, we're actually wasting our silicon. We won't be able to make good use of those. Not only can we not feed them with data, as you saw on the previous foil, but actually we can't even run them at anything like the full speed. I can tell you we could easily make floating point units in the latest 16 nanometer technology that would run at 20 gigahertz. Today you can't buy a chip that runs faster than 3 gigahertz, and in future you won't be able to run a chip that runs faster than 500 megahertz unless we solve this problem. So lower density of floating point units would be a good idea. It would actually allow the floating point units to be faster, and you could use that die area for something else. So this is my thesis. We build machines for particular purposes. Machine learning is surely a massive opportunity and will become a massive market for computing machines. It will justify, without doubt, the invention of new processors. Now, CPUs were designed for Microsoft Word and Excel, I think, mostly. And more recently, they've been used in the web to drive basic string-based web search. GPUs were designed for graphics. They're very good at graphics. They've been deployed with success for dense linear algebra in high-performance computing. But neither of these platforms are suitable for the characteristic compute idioms that we now face, and I've used the acronym IPU here for an intelligent processor unit. And what this needs to be good at is operating on graphs, arbitrary, sparse graphs. And most interestingly, I think that we don't need to bet on the structures and the algorithms that we're using today. Jeff mentioned rectified linear units. For 30 years, everyone assumed expensive sigmoids were the right answer. If we built a machine 3 years ago, we would have devoted a lot of effort to building sigmoid functions. Now perhaps we don't need to. So I think the field is moving too fast for us to bet on any of the specifics today. But what we can bet on is the general theme of massive available parallelism in complex, sparse structures well represented by graphs, executing arithmetic at low precision in floating point, perhaps with some interesting function choices, strong emphasis on being able to move in and out of log domain, for example. And how are we going to do this? Well, I've mentioned on the left, the plan when building a GPU is fill it with flops. Build the biggest chip you can, fill it with floating point units. Put hardly any memory on the chip. All the memory is off the chip, so therefore you need to maximize the bandwidth to that memory off the chip. That was the plan. That's broken. Broken for anything other than graphics. The IPU plan says actually dominate the die area with memory, because that's by far more useful now than the floating point units. Communication will have much more impact on performance in these algorithms than arithmetic will. And communication means memory. So put your memory on the chip. Obviously, you need some floating point engines as well, but they can now be much more efficiently used. So the chip on the right, even though it's got less flops than the one on the left, will probably have a higher performance, and it will certainly be more power efficient. And then what's the role of external memory? That is for bulk transfers only. Bulk on and bulk off. You don't use external memory whilst you're doing a computation. That means it doesn't need to eat any of your power budget. I will leave you with that closing thought. The picture on the left, on the left, by the way, is Colossus. And I think that first ran in 1943. So 72 years of dumb computers, and now we'll build some smart ones. Thank you.
Thank you very much, Simon. Questions, please. So may I ask, can I ask a question? Is it happening or is it not happening?
It's happening. So my company are building such a machine. Can't tell you yet exactly what that looks like, but we are building one. And we have a team who have been working on it for quite a while now, and we expect actually to have silicon for this new machine in about 18 months' time. So we hope that we'll be first with a graph processor And we're aiming to build quite a big, powerful one so that we make quite a big splash.
I really liked what you said. I've got one tiny quibble. You need to add to graphics convolutional neural nets, because when you fetch the weights of a convolutional kernel, you get to use them hundreds of times.
So we're pretty focused on benchmarking our ideas on today's most successful algorithms, even though I don't want to bet on today's algorithms alone. And CNNs are certainly a strong part of that. I think there are lots of interesting things you can do with local receptive fields, for example, that are enabled by getting away from vectors. So already at the moment, you see CNNs with sort of 3x3 or 7x7 convolutional masks, which are obviously not very efficient for 32 wide vector machines. But in the future, why would the masks necessarily have to be square? Why not have hexagonal tessellations of masks, which perhaps reflects more accurately radial fields of interest? In a graph machine, you don't care. The structure can be any arbitrary graph. So I think, for convolutions, there's interesting scope to do things on this machine that are more flexible than on conventional vector machines.
Great. Thank you very much, Simon. Thank you. So our next speaker is Simon Benjamin from the University of Oxford.
Well, hello everybody, and thank you very much to the organisers for inviting me to speak to you. So this is going to be a little bit of a different talk to, I suppose, all the other ones really, because what I'd like to tell you about is a new kind of technology which doesn't yet exist, and it's a matter of hot debate exactly how long it will take until it does exist. Till recently it was a matter of hot debate as to whether or not it could exist, and this is quantum technology. I'd like to talk to you about what that technology might be good for, and in particular, of course, whether or not it will be good for machine learning. So just quickly, the structure of my talk will be to say a little bit about what this phrase quantum technology even means, and the levels of investment that have recently happened, which is very interesting, I think. And then I'll think, I suppose, about the software side of things, to put it in regular language. Assuming that we can build these technologies, what will they do for us? And I'm going to mention some things that we understand now very well that they could do for us, and some things that we don't understand well, and that certainly includes machine learning, but there is some very interesting early work on that. And then I'm going to move over, I suppose, to the hardware side of things, and ask what will these machines look like? What will they be physically? And when can we have them? When can we have one of these machines? And I'm going to argue that the answer to that, really the fundamental issue in the entire field that we've been working on for so many years and that we need to completely crack in order to deploy technologies, is errors. The way that errors behave in quantum systems absolutely governs what we can do with them, when we can have them, whether or not they'll behave themselves. And then finally, I'd like to conclude with an outlook towards the more immediate future, and really a challenge to this audience to help us out. So we'll see how that goes. All right, so first off, what does quantum technology mean? So it's difficult to define, but a reasonable definition is it's a technology that involves harnessing the deeper properties of quantum physics in order to fundamentally outperform conventional devices. So there's several phrases there that we might wonder about. First off, what does it mean to say the deeper properties of quantum physics? Well, quantum physics is, of course, the basic physics on which everything is based. So therefore, I and this computer are already quantum machines. But there are certain phenomena in quantum physics, the ones that really have bewildered physicists and fascinated them for 100 years now, that conventional machines, and indeed we believe organic systems, don't really harness. And it is those aspects that we want to really now get to grips with. When we look at anything that in any sense deals with information, so imaging, sensors, communication systems, and various kinds of computing, if we ask ourselves, what is the absolute limit that we can push this system to, allowed by physics? It always becomes a problem of fully handling the quantum physics. And that shouldn't surprise us, because the quantum physics is what's setting the rules of the game. So to absolutely take any technology to its limit, it always becomes a quantum technology. This is therefore an interdisciplinary field of academia with many thousands of researchers worldwide. It's mainly academic, but certainly not exclusively academic, and there's a growing amount of investment from many companies. Some, like Google and Microsoft, have already made significant contributions to the field. So before cracking on with my talk, I just want to mention that there's recently been a massive investment in these technologies in the UK that went live in December 2014. This was, the big number that you can mention is £270 million. It was announced the previous year. And of that, about 155 million has gone into 4 focused efforts to develop different aspects of quantum technology. And Hermann knows about this very well, because I believe he was involved in the process of selecting which aspects of the technology to push. All right, so first off, quantum computing. The thing I would like to talk about for the rest of my slot is computing, as opposed to, for example, sensors and communication systems, fascinating though they are. So in order to talk about quantum computing, I need to introduce you, if you're not already familiar, to the chap on my right here, which is the qubit, the quantum bit. So on the left, I'm using a light switch to represent a bit, a 0 or a 1. Of course, in our computers, they're represented in a variety of ways. Essentially electrical charges inside devices. But you can think of them as just a light switch, because a bit is designed to be just one of 2 things, and to be stably one of those 2 things. But what quantum physics tells us is that any system that can be one of 2 things can, in fact, be much richer than that. Quantum physics allows, in principle, for something called superposition. And this is the capacity of a system to be in what in our everyday language, we should say, is 2 states at the same time. So then you have the idea of a little entity that can be a 0, it can be a 1, or it can be at the same time 0 and 1, as paradoxical and counterintuitive as that sounds. And when we fully work it through, we find that it's really a very rich object. A single quantum bit, the basic unit of information that's allowed by quantum physics, is much richer than a bit. So here, this thing is called the block sphere, and it's how we picture the basic units of information in quantum science. The points on the surface of the sphere represent all the different conditions that our quantum bit can be in. The North Pole we could think of as corresponding to a bit in state 0, and the South Pole corresponding to a bit in state 1. And those are distinguishable and have the familiar properties. But we're also allowed to prepare our quantum bit in any combination of 0 and 1. And so, for example, the points around the equator there are the ones that have an equal amount of 0 and 1 in superposition, but we can also make a lopsided state that favors 0 or favors 1. And so just to emphasize, this is not saying that it's a 0 or a 1, but we don't know which it is, and we're using this fancy word to describe our lack of knowledge. The physical system really is in a condition which, in everyday language, is 0 and 1 at the same time. It's an exact state of that system. You could think of it as an atom, for example. So then, before moving on then, actually, even before that, the humble qubit already shows us some exciting things. The idea of information being not just 0 and 1, but both at the same time. It also, we can notice a feature that presages the problem for our field, which is that we can't get at that information. If I give you a qubit, and I put it in a particular state, and I don't tell you what that state is, you cannot find that out just by measuring it once, because the act of measuring a qubit will cause it to collapse to the options that you give it, the 0 and 1, or you can measure it in different ways. But you can't tell exactly which kind of superposition I've given you with one go. If I give you lots of copies of the same qubit independently, you can home in by measuring, and then say, okay, now I'm going to measure it a bit differently. Now I'm going to take my next one and measure it a bit differently. And you can zoom in to the information you want to learn. But nature will not let us get at that in one go. Nature knows the state of our qubit, but if we want to find it out so that we can write it down as a piece of conventional information, we'll need several goes at it. And then, so before moving on, the provocative thought about why this might be powerful computing is the following. If we have n bits, we can form a string of those n bits, a series of zeros and ones, which can represent some data for us or a number. If we have n qubits, what does that look like if we have multiple instances of this chap here? Well, if one of them can be 0 and 1 at the same time, then two of them can either be 0, 0, or 0, 1, 1, 0, or 1, 1 at the same time. 4 different states in superposition are then possible, and similarly 8 and 16 and so forth. So the number of different conventional states which exist simultaneously within one piece of hardware goes up exponentially with the size of the device. And the reason that's exciting is that then if we do an operation on, let's start calling it a computer memory, so I might just reach in and perform a small calculation using a series of qubits as my input. Performing that calculation once forces nature to perform that calculation on every element of the superposition at once. So nature will have to do an enormous amount of work in where a conventional computer, in the same circumstances, would have just worked out one thing. Nature will need to work it out for everything in the superposition. This is sometimes called quantum parallelism. It's not actually having a whole set of different chips. It's having one chip capable of being in a superposition and using that fact. Very, very potentially exciting, and yet still the problem of getting the information back out at the end, which limits what we can do. But what can we do? So this is the software. So these are the famous things that we know that a quantum computer can do and that have been very well studied. And the most famous of them probably is code breaking. By taking the core of a machine and allowing it to be in many different conditions at once, we can find essentially the key to a code in far fewer steps than if we had to individually test them one at a time. More formally, code breaking here means factoring big numbers, which is the technique that would allow you to crack the codes that, for example, protect credit card information when it's sent over the internet. This becomes a problem of period finding, and we can do that very efficiently by harnessing this superposition that exists within quantum machines. If indeed we can build them, that's part 2. Algorithmic search, I can say a bit more about that if someone wants to ask me. Simulation, which is, as we've already heard, I think, today, Feynman's original idea for actually inspiring the idea of a quantum computer. Simulation means taking a system we'd like to understand better, a superconductor. Why are superconductors working at some temperatures, but then other materials manage to get to a higher temperature? Can we get to room temperature? That is a problem of simulation, but very, very important for future generations of technology. That could also be approached with a quantum computer. Each of these is then very well examined and studied, but each of them has limitations. In particular, code breaking, whilst dramatic and profound and disruptive, perhaps, doesn't seem to be the kind of thing that has a huge market for it. If we build a quantum computer and then we say, who wants one, assuming it's very expensive, then the people who would want that one for those purposes are people like the security services, or possibly people who want to do bad things like steal our credit card information. So as exciting as that is to computer scientists, and as rigorously studied as it is, it doesn't seem to be the killer app for quantum computing. It's possible that this one here, simulation, as humble as it may sound, is actually a killer app. But we'd certainly like more now that the technology seems to be well on its way. So that leads us to the question of whether there can be such a thing as quantum machine learning. What would it mean? What can we say? Well, what we can say is that this is a relatively much younger area and newer set of ideas compared to these ones, especially compared to code breaking, which has been studied very, very thoroughly. But, of course, a very interesting one. So what I'd like to do, just briefly, without using up too much of my talk, is just to introduce you to 2 particular examples from this emerging field, which then is at the interface of the guys like me who are fascinated by how to build quantum technologies, and the guys like probably the majority of people in this room who are fascinated by machine learning. There's a growing number of people who sit at that interface, and I'm certainly trying to be one of them. Okay, so one idea that made a big splash in the literature that I read involves doing fast matrix inversion using quantum hardware. Oh, that's a lot on that slide, okay. I thought that might come up in steps. All right, so try not to be overwhelmed by this. I'll talk you through it. matrix inversion is something that, if we could do it very fast, would be exciting for a very wide range of fields, including, but certainly not limited to, machine learning. So then I'd like to specialize to this particular problem that you can see just above the green box. Given a sparse n by n matrix A and some vector B, I would like to know the solution to this equation. A multiplying x is equal to b. I want to find out this x, and I'd like to do it as quickly as possible. So from what I'm about to say, there are a number of further restrictions which are non-trivial, but I won't go into them. So we have an algorithm, which I think first appeared in 2008. Here the publication is 2009, by Harrow, Hassabis, and Seth Lloyd. By the way, when you see this thing at the bottom of my slides, archive, ARXIV colon, then a number, if you just type that into Google, you'll get the free version of the paper immediately. And I've tried to cherry pick the publications which give a really clear introduction to the topics that I'm skimming over here. So what these guys were able to show is an algorithm which allows you to solve that problem, essentially. So in the green box, I've written out, tried to summarize what it does. You construct a process, which is a process you're allowed to perform on quantum systems, and you use that process in order to essentially generate a quantum system in state X. And the thing is, it does it fearsomely fast. It does it amazingly fast. Log n, where n is the linear size of the matrix, is the time the thing will take in order to perform this process for you. So that sounds amazing. Look, the top line there, it's an exponential improvement. It seems that's absolutely transformative right there. And people have used that essential trick of matrix inversion in, for example, these machine learning contexts. So quantum nearest neighbors algorithm, support vector machines, among many others. But there is a problem. And it's the problem we still tackle in this field, really, whenever someone comes up with something new. It's getting the information out. Nature knows the answer to that matrix inversion problem very, very quickly, after only a few steps. But we're looking at this set of qubits that contains the information we want, but when we measure those qubits, we will only learn a little bit of it. So unfortunately, if we just take the naive approach, we have to keep doing the algorithm over and over and over again, generating the answer over and over and over again, just so that we get to have a bunch of goes at measuring it. So that is the very non-trivial restriction on this. So what I'm trying to capture for you here is, here's an algorithm which looks very promising on the one hand, but has very non-trivial restrictions which need you to change your thinking. So for example, this might be useful for a problem where you actually only want to know one aspect of X, but you need to, that involves solving for all of X, but you actually only really care about one bit. Then you can have that more quickly. So I don't want to go through a parade of all the different ideas that have come up in quantum machine learning, but I do want to mention one other one, which is at the interface of neural networks and quantum physics. So this was an idea by a team at Microsoft. Again, here are the e-papers. Just tap that in if you want to bring it up. And these guys turned their attention to the question of training Boltzmann machines. That is, complete graphs, not restricting themselves to the kind of layered graphs that we've heard so much about already today, but just going full at the problem of a fully connected graph, for which techniques like contrastive divergence don't work properly. What they came up with was an approach to use a quantum machine to do a sampling process that allows you to figure out the gradient. And they were able to show that this runs, in principle, faster than the best classical techniques that they compared with, at least. Not profoundly faster, as in the previous example, faster essentially by the number of layers in your deep network. So a more modest factor there, but still intriguing and very promising, I think. So this, I think, is a second very exciting work to read and try and understand, and then to take forward. Early days, but I think quite promising. So that's some flavor of the software. Now I want to talk about, it's all very well to come up with these things on paper, but it's only an intellectual exercise unless we can actually build quantum machines. So what are the challenges there, and are we going to be able to do it? Okay, this is where we need to start talking about errors. What is this thing on the screen here? For those who haven't already seen it, would anyone like to take a guess at what this thing is? There's a hand in the corner.
Garbage analytic
There's a man who knows his stuff. I don't think that was a guess, right? So this is a Babbage engine. People have often heard of the Babbage difference engine. This is the more advanced idea that he had, essentially fully programmable computer, the Babbage analytical engine. And this central aspect here, he calls the mill, and is what we might call a CPU. Now, this was a correct idea for a programmable computer some 100 years before we actually realized functioning programmable computers. It was, as far as people can tell by looking at the plans and the notes, it was right and it should work. But why didn't it work? It didn't work because he wasn't able to produce the components of his machine in such a way that they would operate with enough precision that the whole thing can actually function without dying due to friction and so forth. It was a vision that was beyond the standards of its time, and with a little bit of sleight of hand, I would like to say that it's because of the errors in the system, the imperfections. He did not have a theory of imperfections to work out whether or not his machine would be achievable. He just had a go at it, and he did not succeed in realizing the analytical engine. All right, so are we going to face the same problem with our quantum machines? It was once feared by very serious people like Rolf Landauer, for example, that the quantum computing field would have an analogous problem, that we wouldn't be able to control the components of our devices sufficiently well, and certainly they are very hard to control, and that therefore errors would just cascade and eventually cause the machine to produce rubbish. The single most important triumph from the theorist side from the last 20, 30 years was to show that that doesn't have to be the case. You can take quantum hardware and you can make it behave itself, even though the components are constantly misbehaving. To think why that might be hard, apart from the fact that I'm just asserting that quantum systems are difficult to keep them well behaved, consider this. When you try and see if there's an error in a conventional device, your very first move is to look at it. You're going to look at it and say, whoa, does that look right? You're not allowed to look at your qubits. At least, you're not allowed to look at them and actually see exactly what state they're in, because we're in the middle of a quantum calculation involving superposition and so forth. And if you look at your qubits, you're going to collapse them, and you're going to destroy the internal state of it. How on earth are you going to be able to figure out the errors in a machine when you're not even allowed to look at it, let alone the fact that it's very prone to errors? Okay, so there have been various solutions to this, and this is one that is essentially the one that the experimentalists are working towards realizing most aggressively at the moment. This is called the Kitaev surface code. And it's really very simple. Each of these little glowy blobs in my diagram is one of our qubits. It could be it could be an atom, for example, and it's in our superposition of 0 and 1. And here we have a whole array of them. What these guys here are doing is parity checking the 4, or at the edges 3, guys around them. So this guy's job is to test whether the 4 guys around him are in an odd parity or an even parity state. And what we figured out how to do is to answer that question without actually looking at each of them individually. So if I looked at that one and said, that's a 0, that's a 1, that's a 1, that's a 0, it's even parity, no, that would be catastrophic. I would have collapsed these guys. Instead, I look at them collectively and just answer that one question, is it odd parity or even parity? And if I do that, I can actually detect errors as they occur in this grid. So what you see here is a whole bunch of qubits and a whole bunch of dedicated parity checkers running all the time to monitor the parity of their surroundings. And that's essentially how it's done. Now what I have here is, in the last 6 months, these are three research teams who have built different pieces of this device, and it's shown schematically here how big each piece is. You can see that IBM's made a little sort of double parity checker, and these guys at UCSB, now this is the team that just got bought up by Google. Arguably, I think it's very a reasonable thing to assert that these guys are producing the most complex controlled quantum systems for quantum computing of any group in the world, which I guess is why Google bought them up. So you can see that they've done, a thing there. They've got this many qubits. There's actually an error in this diagram. I'm sorry, the white box should slide over one step to the left for real aficionados. But how good is that? I mean, it doesn't look like a very big piece of my diagram. How far are we towards making a quantum computer? Well, that's the bad news. This diagram is smaller than the diagram I would draw if I was trying to describe how to safely and robustly store even 1 qubit of information. I would use all these physical qubits and more to collectively store just 1 unit of information. And so here in the next slide I summarize, all of this is less than 1 logical qubit, as it would be called. A logical qubit then is a protected qubit that even though it's made out of pieces that are prone to error, we can fix those errors, and the logical qubit never suffers an error over the timescale of the calculation. We estimate, and we're trying to improve this number, that we need 10,000 physical qubits in order to achieve 1 logical qubit. That's a scary number. So bringing quantum systems under full control is expensive in resources. Still, can we do it? Never mind that. I mean, it's a big number, but we know that we can produce very scalable technologies these days. It's not an impossible number. Can we actually do that? Well, there's a more subtle question here than sheerly the size of it, and it's the following: that these guys can be made, the entire object can be made to behave perfectly, even though these individual guys are misbehaving, but only if their misbehavior is below a certain level. If they misbehave wildly, then the entire device will not, in fact, be stable. And what is that number that tells us how well the individual guys have to behave? It is 99.9%. That's how well, when we try, so that says how well, when we try and manipulate one of these guys, that's how accurate we have to be, or in other words, how well it has to be behaved in order for us to take this number and turn it into perfection, essentially. Turn it into errors never happen in the course of a calculation. So what we're saying is, not only do we need tons of these qubits, they need to be very well controlled. I can tell you that 10 years ago, 90% would be a tough number to hit in the laboratory. So that looks like we may, and at that stage, we could reasonably say, quantum computers, they might be 100 years away. We haven't got good enough control, and we don't know how long it will take. So the question is, how are we doing now? Given that our target is to control our systems that precisely, where are we at? And the answer is, so I have to put this up as an Oxford guy, that currently the record for control is set by an Oxford team, and it's these numbers. So this is how well we can initialize a qubit, how well we can manipulate it, how well we can do a gate between 2 qubits, and how well we can measure it. And what I hope you'll notice is that every one of these numbers is as good or better than the target that we need. And this one set of numbers is why it is now reasonable to say these machines are going to happen. Because we can control the individual components well enough, and we know how to build them into large structures. All right. So this is, I don't know if I've managed to convey the excitement, but I've been working in this field for, 15 years now, and this is extremely exciting, because it means we're on. We're on for building these technologies. We still don't know how long it will take to get the finished device. Okay, so let me not look at this, because I'm hoping that I have a movie now to show you very briefly, just to conclude with. And I'll just cue that up, and I think the chap up in the booth is going to have a go at... hello, are we? Yes. Oh, here we go. So this is a very simple picture of the kind of thing we'd like to build. We see this mysterious box that we slice open. Each of these gadgets, these railway lines, is a track on which individual atoms can be driven around. What we see here is 2 atoms that are underneath fiber optic cables, and we're causing them to become entangled with each other using pulses of light. Now that is what quantum entanglement looks like, in the opinion of this artist. It's pretty cool. And now we see the atom trundling along its tracks. Over here, it meets another atom and is forced to exchange entanglement with it using another laser pulse. That's the kind of innards that we're thinking about. And then this is pure artist imagination about what the entire machine looks like. Looks like that, apparently. Pretty cool. So what I want to stress is that while that animation is just a pretty animation, the core ideas there, that is to say having atoms, controlling them, moving them around, we now know that we can do. The only question is, how long will it take? So it's a long way from 10 qubits to 10 million qubits. And what we really need to do is find things we can do on the small machines that we will have initially. One solution to that is the one that's pursued by the company D-Wave, which is a different, I would say, more limited approach to quantum computing, but one that can have early success in principle. And the solution I would like to leave up here now as a challenge to the people in this room is the following. I want algorithms that can tolerate small amounts of error happening as we execute them by the nature of those algorithms. So a reminder, this is so far how well we can do. You can think of that as a NOT gate if you wanted to make the classical analog. A 2-qubit gate you could think of as an AND gate, just very roughly to make an analog. That's how well we're able to do the basic elements, and we could probably get it a bit better as well. Now, if that is what you've got to work with, can you come up with an algorithm that when the hardware is getting it wrong at that kind of rate, still leads to an answer that's meaningful? If so, you may be able to outperform classical computers and get early access to this power of superposition long before those of us who are trying to build the ideal fault-tolerant hardware are able to produce it. This, then, would be the kind of thing that can run on machines that we'll have in a few years instead of in 10 years' time. So I guess I'll leave it there. I encourage you to visit this QOPL website for this final thought. Thank you very much.
So I think we have time for one question, if anybody is burning to ask something. If not, we'll well, thank you very much, Simon. And our last speaker, and I hope you'll forgive me, but I don't want to cut Demis short on his presentation, so we'll just eat into the lunch period beyond 1 o'clock a little, so bear with us. So Demis Hassabis, who was co-founder of DeepMind, is now part of Google, which I happen to know is a very unencumbered part of Google. So let's hear from you.
Thanks, Andy. So we've heard, in this session a lot about some cool new hardware. And I really look forward to getting my hands on some of this hardware that's being built. But it's my belief that actually to crack intelligence, we are going to need some big algorithmic breakthroughs as well as hardware advances. So in this talk, I'm going to be talking about software and algorithms rather than hardware. So AI is really the science of making machines smart. And basically, there's two ways of doing this. One is that you can pre-program a solution into the computer and have the computer sort of dumbly but efficiently execute that solution. A second way is that, in fact, you could teach machines, give them the ability to learn for themselves how to solve a particular task. And it's that second type of artificial intelligence that we're interested in and we're working on at DeepMind. Now, DeepMind was founded in 2010. And we were acquired by Google last year. So, and since then, we've been accelerating our kind of research program. Now, the sort of idea behind DeepMind was to create a kind of Apollo program effort for artificial intelligence. And we currently have more than 100 research scientists. So I think it's the largest collection of scientists sort of focusing on this area anywhere in the world. And really, the idea behind it was that to try and create a kind of new way of organizing science. So what we tried to do with DeepMind was combine the best of academia, or at least how it should work in an idealized case. So blue sky ambitious thinking, interdisciplinary collaborations, but then combine that with the best from startup and industry. So energy and focus, and the efficiency and the resources you find in the private sector. And so our mission at DeepMind, it's very easy to articulate, but obviously quite hard to do. And we usually describe it as a two-step process. So step one, solve intelligence. And then step two, use it to solve everything else. So, and although this is a sort of slightly fanciful way of showing it, I really believe that the power of general artificial intelligence that I'm going to show a little bit of later today, in its fullest form, could eventually realize this. Now, how are we going to achieve that kind of ambitious mission? So more prosaically, we're going to try and create what we call general purpose learning machines. So there's two key words there, general and learning. So I already said that the things we're interested in building at DeepMind are learning algorithms. And what we mean by that is algorithms that are capable of learning automatically from raw data, from the raw inputs. They're not pre-programmed or handcrafted in any way. Secondly, we insist on them being general. And that means the same system or same set of algorithms out of the box being able to operate across a wide range of tasks. Now, we call this type of artificial intelligence internally at DeepMind artificial general intelligence, AGI. And the hallmarks of AGI are that it's kind of flexible and adaptive, and it's built to be flexible and adaptive from the ground up. Now, we've sort of call it this term to distinguish it from what is normally thought of as AI, and in fact the majority of AI out there, especially in industry, which we think of actually more as narrow AI. And that type of AI, so things like Siri on your phone, these are bespoke pieces of software that have been created to solve one single task. And I just want to illustrate the difference between these two types of regimes, AGI and narrow AI, with probably the most famous example still of AI or narrow AI. And that's IBM's Deep Blue that beat Garry Kasparov in the late 90s. Now, this is, of course, an amazing technical feat. It was kind of a watershed moment in AI in some ways. But in some sense, actually, I came away from this match more impressed by Garry Kasparov than I was by Deep Blue. Because here is a human with our minds, and Garry was able to compete against this brute of a machine on this very narrow domain of chess. But of course, Garry can also speak 3 languages, drive cars, and even do things like tie his shoelaces. And obviously, this is impossible for a mainframe computer. But that's not only things like driving cars. These are really out of domain. But the interesting thing about Deep Blue is it couldn't even do something strictly simpler, like play noughts and crosses, right, without being totally reprogrammed. So there's nothing in the Deep Blue software or the Deep Blue system that will allow it to generalize to anything other than this narrow domain that it's been pre-programmed for. So in some sense, we don't really view this as true intelligence. And probably even the creators of the system would also probably agree with that. So instead of that, we think about intelligence in this very generalized fashion. And in fact, we think of intelligence in the framework of what's called reinforcement learning. And I just want to briefly describe to you what reinforcement learning is in this simple schematic. So on the left-hand side here, we have the AI system. We call them agents at DeepMind. And this agent finds itself in some kind of environment, and it's trying to achieve a goal in that environment. Now, that environment could be the real world, or it could be a virtual environment. Doesn't matter. Now, the agent only interacts with the environment in 2 ways. So the first way is that it gets observations about the environment through its sensory apparatus. And we normally use vision, but you could use other sensory modalities. Now, the key thing is these observations are always noisy and incomplete. So it's not like a game of chess where you know the full state of the board at all moments in time. The real world is much more messy and complex than that. There are many things you cannot directly observe. So the agent system is built from the ground up to deal with this noisy, unexpected, uncertain environment. And the first job of the agent system is to build the best approximate model it can of the world out there, based on these noisy, incomplete observations, and to update that model every time a new observation comes in. Now, once the agent has a model of the world, what it does with it is uses it to make plans. So it can use the model of the world to roll plans forward, imagine plans forward about what actions it could take and what would be the consequences of those actions. Now, depending on how much time the agent has to think, it can use this model to run various simulations about what will happen. And then the job of the agent system ultimately is to pick the best action that will get it closest towards its goal from the set of available actions available to it at that moment in time. And once it's decided what that action is, it outputs that action, and that action may or may not make a change to the environment, and then that drives a new observation, and this goes round in a cycle in real time. Now, although this diagram is very simple, actually there's a lot of hidden complexity behind this diagram, very complex research questions that need to be solved. But the interesting thing is we know that if you could solve everything in this diagram that I've just explained to you, that would be sufficient for intelligence, for true general intelligence. And the reason we know that is because this is how biological systems learn. All animals, especially all mammals, including humans, learn with reinforcement learning. And it's actually the dopamine neurons in the brain, the dopamine system, that implements a form of reinforcement learning called TD learning. The second thing that we are kind of committed to in our approach with DeepMind was this idea of embodied cognition or situated cognition. And this is the idea that to have a truly thinking machine, it needs to be embedded within a sensory motor data stream. Now, usually when people talk about embodied cognition, if they commit to that and agree with that approach, then they usually start working directly on robots acting in the real world. But we wanted to avoid that because robots are very expensive, they're slow to use, and in fact, you end up spending all your time, if you talk to a roboticist, sort of working on the soldering irons and trying to get the servo motors working, rather than actually concentrating on the intelligence algorithms. So in fact, we decided to start with virtual environments, and specifically to use games. And my previous background was in games, so we knew a lot about games and game systems, and were able to adapt them to our needs. But they're actually the perfect platform for developing and testing AI algorithms. So there are obviously thousands of games out there of varying complexity. They've been built to be challenging to humans, and there's no testing bias because we, as the algorithm developers, didn't develop these games. These games were not developed for AI algorithms. They were developed for humans. And of course, we can increase the gradation of difficulty of the games we tackle to match very closely with the cutting edge of where we are with our algorithms. And if you use games and virtual environments in a proper way, this can be just as sort of valid as using real robots in the real world. Because they have rich data streams, in this case for games, they're pixels, high-dimensional rich data streams, and you've also got to, so you've got to process what's going on there and then make a decision about what action to take ultimately to get you towards a particular goal, whatever the goal of that game is. So we call these kinds of agents that we train at DeepMind end-to-end agents. So they start all the way from the raw pixels and they end up making a decision about what action to take. So we're interested in that entire stack of problems. So I'm going to show you a couple of fun videos of these agents at work. But before I do that, I just want to be very clear to you what you're going to actually see and the significance of that. So we started off with classic 8-bit Atari games from the 80s eras. So these are very iconic games that many of you will be familiar with. But here, the agent, the system, only gets raw pixels as inputs. So it gets about 30,000 numbers per frame, per 50th of a second, because the screen resolution for Atari games was 200 by 150 pixels, roughly. And the goal here that we give the machine is to maximize scores. It's a simple goal. And everything else is learned from scratch. So it has no idea what it's controlling. It has no idea it's playing a game, of course. It has no idea about the rules of the game. All it's getting is these raw pixels as data. And then the last thing is we enforce this idea of generality again. So a single system being able to play all these different Atari games, and there's hundreds of them, out of the box. The same system without any changes. So I'm going to show you a couple of videos. So the first one is Space Invaders, probably the most iconic game on Atari. And I'm just going to roll this video, and the sort of first part of the video shows you what the agent does when it first sees this data stream. So it's literally the first time it's ever seen these numbers, these 30,000 numbers. And you can see it's controlling the green spaceship at the bottom of the screen, and it's losing its 3 lives immediately because it basically has no idea what it's controlling in this world or what it's supposed to do. Now you leave this system playing on a single GPU machine overnight, you come back the next day, and now just through self-play, it's now superhuman at the game. It's better than any human can play Space Invaders. So you'll notice it can't be killed anymore by the enemy Space Invaders. It's worked out the pink mothership at the top there is worth the most points. It does these amazingly accurate shots to get that. And if you, for those of you who play Space Invaders, you'll remember that they get faster as there's less of them on the screen. If you watch carefully the last shot the spaceship fires. So it makes this kind of predictive shot as to where that Space Invader will be in time. So So it's kind of implicitly modeled this world accurately enough to understand what the movements of these enemy ships will be doing ahead of time. So this is my favorite video. It's called Breakout. And in this game, I'm just going to show you more gradations of the agent getting better over time. And in this game, you control the bat and ball at the bottom of the screen, and you're trying to break through this rainbow-colored brick wall, brick by brick. So this is after just 100 games of play, and you can see the agent is pretty terrible at playing this game. It's missing the ball most of the time, but you're starting to get the hang of the idea it should be moving the bat towards the ball. Now, after 300 games, it's about as good as any human can play this. So it almost always gets the ball back, even when it's coming back at very fast angles. So we thought, great, this is cool. But what happens if we just leave the machine playing the game for another couple more hours, couple more 100 games? And to our surprise, what it did was it found the optimal strategy was to dig a tunnel around the left-hand side here. You can see it sort of superhuman accuracy, getting the ball back round the side and getting it behind the wall. And the funny thing is that the amazing researchers, who created this algorithm, they're brilliant researchers, but they're not so good at playing Atari. And they didn't even know about that strategy. So, maybe it's the first example there of something unusual where the creators of a system were actually taught something by their own system. So, this is truly a general piece of technology for learning algorithms for admittedly the limited domain of Atari. And this work was published on the front cover of Nature a couple of months ago, and you can see all the details of that in that paper if you're interested in how the mechanics of that work. And there's even the code online as well if you want to tinker with it. And actually, this algorithm worked. We tested on 49 games, and it was better than humans, professional human game players, on more than half of them. Now, where have we gone with that since? Well, we sort of solved Atari, 80, and these 80s games, these 2D games. So now we need to introduce a third dimension. So we're going towards 3D games now, and we've started with things like racing games, like I'm going to show you in this little video clip, where the same algorithm you saw solving the Atari, we just decided to give it a new data stream, this time a data stream coming from a 3D racing game called Talks, which is an open source racing game simulator. And we just left it, again, driving the car for several hours, several days, I think, in this case, and then we saw what it was able to come up with. And what we found is that, again, just from the raw pixels on the screen, it was able to drive the car better than all the inbuilt handcrafted AIs at more than 200 kilometers an hour around the racetrack, and it even learned to overtaking maneuvers, complex overtaking maneuvers. All, again, I stress, just from the pixels on the screen, just like a human would attempt to play this game. So where are we going next? Well, we're going to test on all sorts of other 3D games. We're also looking at strategic games, so like Go, which has been a big holy grail for AI since chess was solved in the 90s. And then we're looking at things like simulators for robots, and then ultimately we are interested in robots too, real-world robots as an application rather than a development platform. So in terms of the research, I'm just quickly just give you a couple of insights into where we think the challenges are next. So, we've done this Atari stuff. That's the first time, we put together deep learning, the sort of stuff that Jeff was talking about in the morning and invented. We're together with reinforcement learning to create a full learning system end to end, to do something challenging like Atari. But really, that's, of course, only really the first rung of the ladder towards full general intelligence. And the sorts of things we need to crack are capabilities like transfer learning. Now, transfer learning is defined by psychologists who regard it as the key to flexible general intelligence, as being able to apply previously learnt knowledge appropriately to a new or novel situation. Now, that actually breaks down to at least 3 subproblems, all of which are extremely challenging. So firstly, to be able to do transfer learning, you need to be able to identify the salient features in your current environment, and more importantly, be able to work out which of those features you can actually ignore that are not relevant in the current environment. Then once you've found those salient features, you need to be able to re-represent them in an abstract conceptual form. So now divorced from the perceptual details or the perceptual environment you first learnt those features from. And then once you have, you can think of like a library of concepts, abstract concepts in your mind. Then now when you come to a new situation or a new task you've never done before, you need to be able to appropriately select the right prior knowledge from that library of knowledge that will help you bootstrap your performance quickly in this new situation. Now, of course, humans do this effortlessly all the time, but actually, this is something probably almost unique to humans. Most animals are not capable of doing this to any reasonable degree, and it's certainly something we do not know how to do yet well in machine learning. Now, these are all challenging, but I would say the point 2 here, this abstract concept formation, is probably the most key, and I've thought this for a long time. And one of the things I describe here, a quick analogy I can give, is that if we look at how the brain acquires conceptual knowledge, is one of the ways that we use systems neuroscience at DeepMind as inspiration for new algorithmic ideas. Very crudely speaking, you can think of 3 levels of information in the brain: perceptual, conceptual, and symbolic. Of course, it's more complex than this in reality, but this is a reasonable approximation. And I always use, when I talk about this, the example of a dog. So perceptual information about a dog would be how it looks like, what it sounds like when it barks, what it feels like to the touch when you stroke the dog, and so on. These are all perceptual features about dogs. Now, conceptual knowledge about dogs are things that you've learnt through experience with dogs, but are not directly perceptual. So these are things like dogs like chasing cats, they're carnivores, they could be good companions, etc. And then finally, you have the symbolic level, the word dog, the symbol dog, that refers to both the conceptual and perceptual information about the dog. Now, if we look on the right-hand side here and we see what algorithms do we have, machine learning algorithms do we have that are sort of deal with these levels of information, and we find that in the sort of 80s, the kind of what's called good old-fashioned AI now, that was all concentrated on symbolic systems and logic networks. And we know a lot about those systems, but the main problem with them is they were not grounded. So it was called the symbol grounding problem. So it was all very well creating these elaborate databases of logic networks of relations between symbols and other symbols, but what did those symbols actually mean when that system interacted with the real world? And there was no way of grounding those symbols in terms of sensory motor reality. On the other hand, though, these very exciting advances that happened in the last decade with deep learning have allowed us now to deal with messy, real-world data, perceptual data like images or speech, and be able to process those quite well for things like classification tasks. But there's a missing gap in terms of trying to get these deep learning systems to be able to actually output what we would call abstract conceptual knowledge, not just highly processed perceptual knowledge. And this missing gap here is sort of synonymous with the conceptual knowledge layer in the brain. And we don't know how to do that yet in machine learning. But we have some clues from neuroscience, and those clues are actually, it seems like an area of the brain. It's not just this area of the brain, but one critical area of the brain that's involved in concept formation is called the hippocampus, which is here in pink in the center of your brain. And it turns out, so I did my PhD at UCL just up the road, and I studied the hippocampus, and with my colleagues there in Eleanor Maguire's lab, we found that actually patients that have damage to this area are not able to form new conceptual knowledge. They're able to access concepts they formed prior to their disease or their damage to this area of the brain, but they cannot form new concepts. So it seems as though the hippocampus is performing some critical gateway function to the acquisition of new concepts. Now, unfortunately, I haven't got time to go into how the hippocampus does this, but we are mimicking some of the features of the hippocampus in terms of trying to understand how we might be able to do this in artificial systems. Now, interestingly, a second thing that the hippocampus is very important for is memory. Without your hippocampus, basically, you have amnesia. And this is what happens in Alzheimer's disease, which actually attacks the hippocampus as one of the first areas. You end up amnesic. And this is one of the inspirations behind a new advance that I'm very excited about that we're doing now at DeepMind, a new piece of technology where we're trying to add memory, the idea of read-writable memory to neural networks. And traditionally speaking, neural networks haven't had this off-board memory that they can utilize. And so I haven't got time to go into the details of this algorithm. I'm just going to give you a quick cartoon of the basics behind it. So what we start off with is a classical computer on the left-hand side here, and we use it to train up a recurrent neural network that has this additional memory store. And this memory store is a special memory store in that it's fully differentiable. So you can actually use methods like stochastic gradient descent that Jeff was talking about earlier on today to train this kind of system end to end. And what you end up with is what we call a neural Turing machine on the right-hand side here. And we call it a neural Turing machine because by adding memory to neural networks, you now have all the components necessary for a true Turing machine that Alan Turing defined in the 30s and 40s. And so you might say, well, okay, so what's the point of this convoluted thing if you had a classical computer at the beginning and what we ended up with basically a classical computer? So why did we do this? Well, the power of the right-hand side is that this is a learning classical computer. So traditionally, with a normal computer that we use every day, our Apples, iMacs, and so on, you have to program a solution. You have to program it directly with solutions using all these programming languages. And that's slow and difficult. But instead of that, because this is a neural network that is mimicking a classical computer, it can actually learn programs by example. So we've used it, and we published an early archive paper on this, where this type of neural Turing machine could learn simple programs like sorting algorithms just by example. And so what it does is you can give inputs of unordered, jumbled up numbers, and you show it outputs, the outputs you want it to create of nicely ordered numbers, small to big. And you show it various examples of this, maybe several hundred, maybe perhaps even several thousand of these input-output examples. And then now you can show it a new input of new jumbled up numbers in a way that it's never seen before, and it will automatically sort those numbers, as if you had directly programmed a sorting algorithm. Now, of course, sorting algorithms are kind of like the 101 of computer science, and we are now in the process of trying to scale up these systems to learn much more interesting, much more complex programs like graph problems. So just very quickly to sort of finish off, so there's obviously, we're thinking about applications too, although DeepMind is primarily about research. There are very interesting applications on the horizon. The key thing about general learning algorithms is that they really are general, so you would expect they should be able to be applicable in many, many domains. Some of the things I'm most excited about are areas of healthcare that I think people are going to talk about later in this afternoon session. The idea of AI scientists helping with that. Personalization, predicting user journeys to make recommendation systems and other things better. And then finally, things like robotics, household cleaning bots, elderly care bots, these kinds of general purpose robotics. And I just want to conclude a sort of a more philosophical level, how I see, why I think general AI and why I spent my whole career, whole life working on these types of technologies, is I see two big challenges for society today that confront us. And it's to do with information overload and system complexity. Everywhere we look now, we're just deluged with information. The issue, big data is, of course, a big buzzword. And the issue is not the fact of collecting the data. We have tons of data. We're collecting, sort of doubling that amount of data every year. But the problem is finding and dealing with, finding the insights and actually dealing with that volume of data. Both on a kind of industrial level and a personal level. So personalization technology is supposed to help us as individual users with dealing with this deluge, but it doesn't work very well because it's usually done by the averaging of crowds and sort of with collaborative filtering and other technologies. So you end up with a kind of median result rather than something specific to you as an individual. And the second thing is system complexity. As the Royal Society of Scientific Establishment, the big science would like to, as a society, we'd like to have made much more progress. Some of the big challenges facing us today: climate, disease, macroeconomics, even things like large-scale particle physics. All of these systems now are actually big information and data challenges at their core. And we might have to come to, the sobering realization that even with the smartest set of humans on the planet working on these problems, these systems may be so complex that it's difficult for individual human scientific experts to master everything they need to in their lifetime and still leave enough time for them to also innovate and advance those systems, those understanding of those systems. So it's my belief that we're going to need some assistance. And I think AI is the solution to that, this kind of general AI. And the reason I work on this rather than working on any of these specific scientific problems is that I see this kind of AGI as a kind of meta solution to all of these problems. If we can crack what intelligence is, then we can use it to help us solve all these other problems that we would like to understand better. Now, at Google, Google's mission statement is to organize the world's information and make it universally accessible and useful. And the way I interpret that is that we are trying to empower people through knowledge. And if you think about general AI or AGI, it perfectly fits with this mission because AGI is really a process that converts unstructured data or information into useful, actionable knowledge. Now, I know, again, some people are going to talk about this, Nick Bostrom and others, about the ethical side of all of this. And I would just want to say one statement here about, as with all new powerful technology, of which, of course, something like general AI could be one of the most powerful, we must use it responsibly and ethically. We set up an ethics board at Google DeepMind to start investigating this, and there's a lot of research to be done here. But I would say that, just as with all new technology, the technology itself is neutral. It's down to how we as a society use it that will determine whether it's beneficial or not. And finally, I just want to leave you with a thought. As a neuroscientist, I'm also, of course, very interested in the human mind. And I think by trying to distill intelligence into an algorithmic construct, like we're trying to do at DeepMind, and then comparing that to the human mind, I think that will help us better understand the unique and special aspects of us as humans, like creativity, dreaming, and perhaps even consciousness, and perhaps get us towards unlocking some of the mysteries as to what those mechanisms behind those capabilities are. So I just want to leave you with a quote from Richard Feynman, one of my all-time scientific heroes, who said, "What I cannot build, I do not truly understand." Thanks for listening.
So I hope you'll forgive us, but we'll move on to lunch and people can grab you. Thank you very much to you and to others for a very interesting session. Bloody brilliant. Bloody brilliant.